All right, so welcome and thank you for attending my master's thesis seminar. Today I'll be presenting our work in developing CADC++, a paired weather domain adaptation dataset that extends the existing Canadian adverse weather driving conditions dataset, which is also referred as CADC. So CADC was built to have only snowy scenes, but we developed CADC++, an extension to match each CADC sequence as closely as possible with a sequence from clear weather to enable domain adaptation research. In this work, we mainly focus on LiDAR-based 3D object detection for autonomous driving applications. So just a little bit of background for those who are not familiar with this line of research. LiDAR sensors generate 3D maps of the environment, commonly using the time of flight principle. They emit laser pulses and measure the time it takes for them to return after reflecting off objects. That time of flight can be then used to calculate the object's distance and subsequently be converted into a 3D coordinate in space. Combined with the received power, the 3D coordinate then constitutes a point in a LiDAR point cloud. An example can be shown on the right. So under clear weather conditions, LiDAR sensors can generate accurate scans of the environment, but under adverse weather conditions, their laser pulses might be affected. Specifically, hydrometeor particles like fog, rain, or snow can cause signal attenuation and backscattering. Many studies have shown that those effects can result in a point cloud with overall weaker intensity values, potentially a fewer number of returns, and extra spurious points at closer ranges, like here. So while many prior works have studied the effect of snow on LiDAR point clouds, research on its impact on 3D object detection remains limited. To be able to objectively evaluate the impact of snowy conditions on 3D detectors, domain adaptation experiments must be done on paired datasets, where snow is the only varying factor with otherwise identical scenes. Then we can train separate models on each domain and evaluate their performance on the alternate domain to observe the impact of snow on 3D object detection. In practice, however, collecting data in different weather conditions while maintaining identical scenes can only be achieved in controlled environments like weather chambers. But that would produce unrealistic data sets that are underrepresentative of real-world driving conditions. So we decided to slightly relax the requirement of having paired sequences exhibiting identical scenes and allow for slight differences as long as they were recorded on approximately the same roads. Unfortunately, current autonomous driving datasets with 3D bounding box annotations don't meet our requirement for snowy weather-based domain adaptation. They either only have data in clear weather or additionally only include rain. Some datasets like CADC focus on snowy conditions but then don't provide data in the clear weather. Dense is the only dataset that offers data in both weather, but there aren't enough frames in each domain to train a detector. Its snowy frames are only half the size of the kitty datasets. Also, its sequences are not paired or not necessarily recorded on the same roads. So to fill a gap where there isn't enough data in the alternate weather domain, some resort to desnowing or snow simulation methods to generate synthetic data. To generate clear weather data, either statistical denoising or learning-based snow segmentation algorithms can be used to desnow the snowy data. The methods aim to identify and discard the additional spurious points introduced by snow that might cause a 3D object detector to predict a false positive. However, they don't realistically address the effects of signal attenuation, missing returns, or handle accumulated snow. Others use physics-based snowfall simulation to generate snowy data from clear weather. They parameterize factors like snowflake density, size distribution, and snowfall rate to account for the effects of backscattering and attenuation. However, despite their efforts to capture the effects of airborne snowflakes, fallen snow that accumulates on roads and objects was not modeled. So in the end, while generating synthetic data can produce paired sequences with identical scenes that only vary in weather conditions, and also it doesn't require any extra labeling because the scenes are identical, simulation nonetheless introduces an additional domain gap that cannot be distinguished from the weather one. So since there was no existing paired dataset for LiDAR-based 3D object detection, we decided to extend an existing snowy dataset like CADC with some new cleared weather data. This was possible because our group co-developed CADC, so we had access to some unused and unlabeled clear weather data collected using the same vehicle platform on the same road. So before I give more details on our clear weather data, let's first have a look at the CADC dataset. CADC was the first autonomous driving dataset that targeted snowy adverse weather conditions. It was recorded around Waterloo and contains both LiDAR and camera data with 7,000 frames annotated for 3D object detection. It was also the annotation categories are 10 commonly seen objects on driving roads. So here's an example of a CADC sequence. Might be laggy, I'm not sure, but I'll let it run a little bit. We can see there's a lot of snow on the road. Some scene sequences are heavier, some sequences are lighter on the snow, but it generally has snow. Now, during CADC's development, there was also a bigger data collection effort that recorded about 1,000 kilometers of driving data, not only in Waterloo, but also in Kitchener, Cambridge, and Guelph. These recordings include snowy, sunny, and cloudy conditions. In this work, we consider both sunny and cloudy conditions as clear weather. So in the end, we have a little over 400 clear sequences to choose from around the region of Waterloo if we don't consider those further than Kitchener. So we show the clear weather data in gray here. While the majority of CADC sequences are covered by the clear data, marked in black, the ones marked in red are unfortunately not covered by clear. For these ones, we'll be manually matching them to something of a similar domain. One interesting characteristic about our clear data that might not be the typical in other clear weather data sets is that they were recorded in the winter, with some drives happening only one day apart from the CADC drives. So this characteristic helps minimize any potential domain shift that comes from other environmental factors when we try to match with CADC. So here is an example clear weather sequence. It's still in the winter, but the snow cover is significantly reduced or non-existent, and it's either sunny or cloudy. So after selecting the CADC++ sequences, they required annotation, but annotation using human labelers is very expensive, and we couldn't afford ground truth for all the frames due to budget limitations. To mitigate this, we decided to sparsely label the training set and then explore a method that can automatically generate high-quality labels for those unlabeled frames. The validation set still needs to be fully labeled to ensure accurate evaluations. So in the end, we had a budget to label every 10th frame of the training set. So there are different ways we can auto-generate labels. One method is to use a model that was pre-trained on some other data set. Then we'd run inference on the unlabeled frames to generate pseudo-labels. We refer to this as pseudo-labeling. Another way is to train a model only using those sparsely labeled frames and then generate pseudo-labels that will be used to train the model again. This method is referred to as semi-supervised learning. Moreover, we can take advantage of the sequential nature of the data and also of the fact that the frames were sparsely labeled at a fixed interval. And then we can use interpolation for the intermediate frames. Lastly, we can also train a model that learns to automatically label objects using whole object tracks from both past and future data. This approach is referred as track-based auto-labeling, but current methods solely rely on fully supervised training. In this work, we explore track-based auto-labeling methods that work specifically for sparsely labeled data, using a mixture of these techniques. Next, I'll briefly show a typical track-based auto-labeling pipeline for fully labeled data based on the current state-of-the-art control. So here's a typical pipeline. It consists of two main stages, a first stage that aims to initialize object tracks, and a second stage that aims to learn to refine object tracks. Now let's break it down by the three main components. First, we have a pre-trained object detector that infers on point clouds and outputs initial object detections. Then those detections go through a multi-object tracker that associates object instances into unique tracks, which refer as proposed tracks. Now, in the second stage, the refinement module uses the proposed tracks to crop out and aggregate tracks of point clouds and use both alongside the ground truth tracks to learn to refine the detection tracks. So the second stage is mainly track-based. Now together, this pipeline learns to detect more accurately by refining object trajectory. Okay, so that concludes the background section, and now I will go into more detail about how we've developed the CADC++ dataset. So as of now, we have the sets of CADC sequences shown in different colors on the left, and the sets of sequences from Clearweather shown on the right. And we aim to figure out how we can maximally match each CADC sequence with a similar length one from the Clearweather. We want to match the two domains, so ideally the best match is the one that covers the same stretch of road, travels in the same direction, and even in the same lane. This way, the viewpoint, driving environment, and driving behaviors can remain as close as possible. However, there might not always be an exact match, so we devise a method that can then pick the next best candidate, such as from an adjacent lane, traveling in the opposite direction, or from an adjacent road segment. If at the end of our selection there are more than one candidate, we'll manually pick the scene with either a similar domain or more traffic agents, given that it might be more interesting. So after we match sequence by sequence, the resulting CADC++ should be comparable in size with the original CADC and also have a similar number of sequences. Moreover, each CADC sequence should be paired with a unique CADC++ sequence to ensure that the training and validation sets maintain similar sizes and distributions. Now let's dive into our matching methods. So a sequence gets recorded at the Lidar's operational frequency. So the coordinates of the traveled path are equitemporal. However, to be able to compare two sequences in space, we need to compare their coverage in space. So we need to first create spatial models for them, where the points are now equidistant. Once a discrete spatial model of each snowy and clear sequence is obtained, we can then calculate a longitudinal overlap ratio between every pair of snowy and clear sequences. Here in red, we have an example snowy sequence S from the set of CADC sequences, denoted by capital S, and next to it in blue is an example of clear sequence C from the set of clear sequences, capital C. The points are coordinates from their respective spatial models. Now we want a ratio that can tell us how much the CADC sequence is covered longitudinally by a given clear candidate. And obviously, the higher the coverage, the better. So we define a function called cover, which computes the fraction of points in the snowy sequence that are within a specified distance theta of a point in the clear sequence. And we calculate this overlap ratio for a range of such distance thresholds. Here we have 1 meter, 2 meter, 4, 8, and 16. So smaller threshold like 1 and 2 meters ensures that it's within the same lane, given the average lane width is 3 meters. A 4-meter threshold accommodates for trajectories in other lanes and potentially the other traffic direction. And depending on the road size, 8 and 16 meters consider all lanes from both traffic directions. So now for each distance threshold, we consider the best covering candidate and try to further refine the set of best candidates, denoted by capital C S star. So here's how we refine each candidate. We prefer candidates that are in the same lane and that completely cover the snowy sequence. If there aren't any, we then pick those that are anywhere on the same road and cover most of the snowy sequence. Then, if there still aren't any, we pick a candidate as long as it covers a bit, if that's the only option. If that's not the only option, then we pick candidates that are consistently the best choice for more than one distance threshold. Lastly, if none of these filters match, we manually select the most matching one and our interesting sequence. So CADC sequences with 0 candidates are also manually assigned a match from a different, sorry, did I just heard like a meeting sound? Did I drop out of?
No, I think Makey, I think there was one of your colleagues joining late.
Oh, okay. Sorry, I thought I was talking to myself. All right. All good. So, yeah, I was just saying how if there's no candidate, then we manually assign a match from a different location but a similar domain. So we try to fit the driving scene, such as type of street or traffic density. So yeah, those are the criteria we use to select a sequence. But now that we have the sequence, we need to then select the overlapping part in that sequence and discard the rest. However, after doing that, the useful segment might not have enough frames because we ideally want each sequence to have 100 frames to match the same length in CADC. So how do we handle the sequences that aren't long enough? We can increase the sampled frames by increasing the sampling frequency up to 10 Hz because that's the LiDAR's operational frequency until we get 100 frames. If that's not enough, we can then extend the endpoints to make the segment longer until we reach 100 frames. But the other scenario, alternatively, is a sequence might have too many frames, even though the travel distance is the same, because vehicles might drive faster in clear weather. So in those cases, we select the covering segment, but then we can downsample the frames, going down to frequencies like 2.5 or 2 Hz. Here are some examples of our final matched pairs. So in blue, we have CADC sequence, and in orange, we have the matched and trimmed clear sequence. In the legend, each sequence is assigned a number, like CADC 51, clear 6, as its unique ID. Below the sequence name, we indicate the number of frames, like 95 frames, and the sampling frequency at 3.3 Hertz. For CADC, most of the sequences have 100, some are exception, but for clear, we try to have minimum 100. And Dmax is the distance between the furthest 2 points between the two sequences. So in figure A, it shows when a segment of a clear sequence was able to match exactly a CADC sequence while sharing the same sampling frequency of 3.3 Hz and satisfying the 100 frame requirement. In B, it shows that an example where it matches in length also, but its sampling rate had to be increased to 5 Hz to reach 100 frames. Figure C, however, only has a match for part of the CADC trajectory. Therefore, the clear trajectory had to be extended beyond the closest matching frames to achieve a frame count of 100. And that increases the maximum distance discrepancy, Dmax. But that was necessary since that was the best candidate and the highest possible sampling frequency of 10 Hertz has already been reached. So we couldn't shorten the sequence further. And these type of adjustments are also applicable when the CADC sequence are static, like in D. So here are some statistics about how our CADC++ compared to CADC after we've done the one-to-one sequence matching. We can see that the clear weather dataset, CADC++ has overall more cars, which is expected since people generally like to avoid driving under snowy conditions. But the other categories, such as truck, bus, and pedestrian, also seem relatively well matched. Next, we show some distributions for cars because that's our majority class. So on the left, we are plotting on a log scale the distribution of point count per labeled 3D bounding box. And on the right, we have the number of objects per frame, which is also like the object density per frame. So it's important for these distributions to match, since it might be harder to train a model on objects with sparser points or scenes with a different traffic density. Fortunately, these distributions are pretty close. Next, we try to obtain some speed and motion distributions by estimating the average speed of full object tracks based on a threshold of 0.2 meters per second, since sometimes there's a drift in point clouds. We categorize them as either stationary or dynamic. The distribution of average speed per track is plotted on the left, and number of stationary and dynamic objects are plotted on the right. We can see that there are slightly more stationary cars in CADC, possibly due to the smaller number of parking lot appearances in the cleared sequences, but the overall number of dynamic cars are similar. It might be worth noting that if a 3D object detector has a bias on static objects, this might slightly skew the results. Okay, so that concludes our section on the dataset development. Now we will move on to the second part of our work, where we devise some track-based auto-labeling methods to tackle sparsely labeled data, since CADC++ training set had to be sparsely labeled. So current state-of-the-art auto-labeling requires sequences to be fully labeled because they rely on full supervised training. But is that really needed? If not, can we work with sparsely labeled sequences? If yes, then how sparse can we go? So this work aims to find how we can generate the best possible pseudo-labels while using the fewest number of human-annotated ground truth. We also want a method that yields balanced performance on both stationary and dynamic objects to avoid amplifying the existing bias towards stationary objects in common datasets. So here's an overview of the methods and resulting models that we train. We classify them by their architecture and supervision types. Our experiments have either one or two training stages. It's either a base model that just performs object-based supervision, or it's a control model that takes the output of a first stage, passes through a tracker, and trains with track-based supervision. Object-based supervision means that individual object instances are supervised independently, and track-based means a track of detections is supervised with a ground truth track. So we experiment with 5 different methods, which consist of our full supervision baseline, sparse supervision, and 3 different types of semi-supervision that involves either interpolation, semi-supervised learning, or a mixture of both. Full supervision means that all labels for all frames and all sequences are human annotated and available during training, hence denoted by 100%. Sparse supervision, however, only has access to the ground truth labels of a small number of evenly distributed frames within a sequence, which we call sparse labels. Finally, semi-supervision involves training on a mixture of ground truth labels and pseudo-labels, and the different methods specify how to create these pseudo-labels. We'll go into that more details for each method, but now let's first talk about how we set up our experiments. So we decided to use the Waymo dataset for both training and validation because it's large scale and also fully labeled. So we use all of their 1,000 sequences, but subsample the training set at different frequencies to experiment with different levels of label sparsities. We also use their official evaluation metrics to benchmark our methods. And as of how we subsample their labels within a sequence to simulate sparse labeling, we first trim all sequences, which are usually around 200 frames, to 169 frames, a nice number that can be divisible to subsample at specifically 12359 frames per sequence, which we'll refer to as FPS. So for 1 frame per sequence, we choose the middle frame. Then for 2 FPS, we choose the first and last. And for 3 FPS, we choose first, middle, and last, and so on until we have 9 frames per sequence. This way, our experiments can be a subset of each other and the results can build on top of each other. So for each of the 5 chosen sparsity levels, we then train base and control models according to these supervision techniques, except for the baseline, which have to use the fully labeled data. Now let's look into more in detail each of the methods and their architectures. So fully supervised models are used as baseline to show the upper bound of what is achievable when the highest level of human annotation is available. So for here, a base 100% model, it's straightforward. It uses all of the available point clouds and their corresponding labels and trains as we normally are familiar with object detectors. But for control, here we show the same architecture we saw earlier. It uses the already trained base 100% model to predict detections. It then passes them through a multi-object tracker to obtain proposed tracks. And then the refinement module uses the fully labeled ground truth that needs to be converted into tracks to supervise itself and then output refined tracks. Now, for sparse supervision, a simple way to handle sparsely labeled data is to use only the sparse labels and their corresponding frames. So, sparse labels are obtained by subsampling, as we've shown previously. And since base detectors supervise each object independently, it can be trained using only the sparse labels without any architectural modification. We just need to train for longer to adjust for the loss of training samples. The refinement module, however, does not natively support sparse supervision. It's designed to have object detection at the Lidar's operational frequency of 10 Hz, and tracker is also tuned to work with 10 Hz. So we keep the detection at 10 Hz, but make our own adaptation to the native control architecture to accommodate for sparse supervision. So I won't go into the details in this presentation, but basically we utilize all the available point clouds for feature extraction, and then only in the supervision step, we use sparse ground truth tracks. So this way we can perform sparse supervision while still making use of all the available sensor data. Next, semi-supervision is a standard technique to make maximum use of limited ground truth. The idea is to supervise with sparse ground truth for frames where they're available and use pseudo-labels for the remaining unlabeled frames. Here, we experiment with 3 different ways of obtaining pseudo-labels. First, we try using interpolation, then pseudo-labeling using a base detector, and lastly, we adopt a hybrid approach that involves both techniques. Let's first look at how the interpolation works. So since these sparse ground truths were uniformly sampled in time, a simple way of obtaining pseudo-labels for the unlabeled frame is to interpolate the intermediate ones. Small details before interpolating, we need to first convert them into world coordinates and also unwrap the heading angles because they were originally provided between minus pi and pi. And then depending on how many data points we have, we can adaptively interpolate using the appropriate degree of interpolation. So we do a cubic spline interpolation if a track has at least 4 frames, quadratic spline if 3, linear if 2, and none if only 1. Also, we only interpolate the object's bounding box center and heading angle while keeping the object's ID and dimensions the same throughout the entire track. For the base model, here base int, we train using both the sparse ground truth and the interpolated label after we convert back the tracks into frame-based labels. But for control models, we can directly supervise using the tracks for interpolated labels merged with sparse ground truth. Now, an alternative method to obtain pseudo-labels is to run inference with a previously trained model, such as base sparse. Then we select confidence pseudo-labels from those output detections and train in combination with the sparse ground truth labels. We denote this approach by SSL. So for base SSL, we use the pre-trained base sparse model here that we trained before, and then select the pseudo-labels with confidence scores above 0.5, and then we train it again. The process is similar in control SSL models. However, unlike the base SSL, control needs to supervise with tracks. But pseudo-labels are not annotated by humans and don't have unique ID associated with them. So we then use the tracker to obtain tracks from those detections, and then we can supervise a control SSL model. Now, lastly, for the hybrid method that uses both interpolation and semi-supervised learning, we hypothesized that stationary object can be interpolated easily with minimal error, since they don't vary significantly in speed or trajectory shape. But in contrast, dynamic objects may exhibit more complex motion, resulting in poorer interpolations, especially as the sparsity intensifies. So we then explore using interpolated labels for stationary and pseudo-labeling for dynamic objects. So we don't classify a full track as stationary or dynamic because the object might stop temporarily, then drive off. So we need to split the track into segments. So we estimate a track speed using the available sparse ground truth labels and split the track into different segments if the motion changes from a stationary to dynamic or vice versa. So we consider a segment stationary if it's below 0.2 meters per second, similar to how Waymo defined it in their evaluation metric. So for all the stationary segments, we can interpolate the intermediate timestamps. For the dynamic segments, we first obtain pseudo-labels for the entire scene, then we discard those that overlap with the interpolated one using a 3D IOU threshold. Finally, we then combine the pseudo-labels for dynamic and stationary with the sparse ground truth to create mixed labels, then supervise the base int SSL model. The process is similar for control int SSL, except it now requires the mixed labels to have track IDs. So we pass into a multi-object tracker to obtain tracks, and then it can be supervised the same way. So that concludes the details of each of our method. Let's now look at the main results for a training experiment. We break it down by motion in the two right figures, and the overall combined performance is shown on the left figure. Note that 80% of the validation vehicles are stationary, so the overall results are mainly skewed toward the stationary results. While one could take advantage of this imbalance to improve the overall performance, we don't want to bias it and want instead a balanced performance between stationary and dynamic. So each of the different methods is shown in a different color, and base results are shown in a slightly lighter version than the control equivalent. And we don't include results of base int SSL and base int because we want to reduce clutter, but they show the same trends as their corresponding control results. So the baselines are shown as straight lines to act as upper bounds of what's achievable with fully labeled data. And straight off, we can see that most of the control results exceed the base counterparts, since they exploit knowledge from both the past and future. Now let's first analyze the base results. So we see that while the performance of base sparse decreases with the number of frames per sequence, its performance at 9 frames per sequence is very close to 100% baseline, even though that's only using 4.5% of the data. So on the other hand, base SSL in green is more robust to data becoming sparser, but it doesn't do as well at 9 FPS. So that shows that pseudo-labels do contribute valuable diversity, but then at some point they are still low quality and can introduce false positives that confuse the model. Now, if we look at the control performances, we see that while interpolation in red works well for stationary vehicles at higher label frequencies, it completely fails for dynamic objects and also stationary ones at lower frequencies. Whereas control sparse, here shown in blue, demonstrate the best performance in stationary, but also fails and deteriorate in dynamic. And that's similar behavior than the base results. So since we observed that the dynamic performance is pretty poor, we experiment with control SSL and also control int SSL to see if that can balance the performance. So control SSL in green can definitely overcome the imbalance by doing much better in dynamic, but at the expense of its stationary performance. And this is expected because pseudo labels, again, are not that accurate and might introduce false positives. So lastly, we evaluate our hybrid approach, control int SSL in orange, and it's the highest performing method for dynamic vehicles and also greatly improves from the green SSL results. It, however, is still not as accurate as sparse, with pseudo labels inevitably introducing some confusion. So in the end, we propose using our hybrid approach for a high and balanced performance. And at 1 frame per sequence, because we can't interpolate, then control SSL would be the best choice. So we note that even at 1 frame per sequence, which is only 0.5% of the labeled data, our control SSL still outperforms the base 100% baseline, which was trained on all fully labeled sequences. So before we conclude, here are some visual examples of how our method performs compared to the standard detector. On the left are detections from a standard detector that use fully labeled sequences. We can still see some jerkiness in both stationary and dynamic cases. On the right, we have refined detections from our control int SSL that only used sequences labeled at 3 frames per sequence, which is only 1.5% of the training set. So we can see that the tracks are much smoother for both stationary and dynamic cases. All right, now that we have a sparsely labeled CADC++ dataset that pairs with CADC, we've also developed methods that auto-label the remaining unlabeled frames. We can then use this paired dataset for domain adaptation research. So as future work, we can finally assess the impact of snowy conditions on 3D object detection. We can also benchmark and devise more accurate learning-based desnowing methods or develop some weather-based style transfer methods for point clouds, either from snowy to clear or clear to snowy. And that concludes my presentation. Thank you all for listening.